Hello, and welcome to this talk on machine reasoning. Before we start, I just want to touch upon few points of general hygiene. Well, let me just read through these. Well, this presentation and related content is entirely an individual's own interpretation, and hence it could be different. There could be different opinions and inferences on the same topic from different individuals. And I would encourage if you can collaborate on that if you have so by providing those in the comment section. Second, the any cross reference to any existing published content if have been used in this its source shall be mentioned. Third, the most important, all the readers are requested to provide their valuable feedback, comments, critics via the comment section, or you can write to me. And if you like the content, please do subscribe the channel and hit the like button and also the bell icon if you want to receive any updates or notifications to for the content which shall be updated in the upcoming future. I will also publish links related details in the description of the video. So let's proceed. Before we go into the details of like what exactly machine reasoning is all about, I think the most important part to touch upon is why do we need machine reasoning or why is there machine reasoning at all? Well, I started doing a sort of research study on various cognitive streams and eventually came to know when we say cognitive, it is much more than just most popular concept of machine learning. It could be related to robotics or say deep learning and those concepts of machine learning, and it could be even IoT or anything else coming together. And then came across the concept of machine reasoning. Well, to me, if I have to correlate, I can say that intelligence is like an onion. It has many layers. Once we understand one layer, we find that it only explains a limited amount of what intelligence is about. We discover there's another layer underneath, and back to our research intuitions, we go to figure out how it works. In our recent exploration of the intelligence of voice assistants, we were teasing at one of those next layers understanding. That is, knowing what something is, recognizing an image among a category of concepts, converting an audio waveforms into words, identifying patterns among a collection of data, or even playing games at advanced levels is different from actually understanding what those things are. So it's a simple theory of DIKUW. As it says, it starts from data. Data is the least fragmented part which exists in bits and bytes, or maybe um, in some sort of variable through which we can store. And then there is something called information, which basically tells or describes the what part of it or what that data is. And then comes the knowledge. So knowledge is something which basically adds meaning to the data, or one can say the inferences out of it. So for example, I can have a picture of data which is an information or piece of information containing the piece of data which is free. Now, whether this picture of an object is called tree or something else is the knowledge. And then comes the understanding part, like why it exists, what is the need for that, right? And the future is where the wisdom comes. So now we know that there is data. Now we have inferred it into knowledge. We have built our understanding. What should we do with that knowledge? Or what should we do with that understanding? And that is where wisdom comes in. And that's like answering new questions after receiving that data into the form of knowledge and making our understanding. One more thing, as I said, playing a game at advanced level is different from actually understanding, or is actually different from playing a game at basic level. And there comes the importance of understanding. This lack of understanding is why we get hilarious results in voice assistant benchmarks, but also why we can't truly get autonomous machine capabilities in a wide range of situations. Without understanding, there's no common sense. Without common sense understanding, machine learning is just a bunch of learned patterns that can't adapt to the constantly evolving changes of the real world. And that's why we say when we talk about cognitive technology, alone machine learning is not going to fulfill the need, and we need some reasoning for the stuff we learn. Now let's see what exactly is machine reasoning is all about. So machine reasoning is a concept of giving machines the power to make connections between facts, observations, and all the magical things that we can train machines to do with machine learning. So it's like as we humans do, we in our brains we make some sort of network or some sort of connections between certain observations. And the similar way we say that it is a concept of giving them this power to make connections between observations or between facts and anything through which they are getting learned. Now, for example, sports provide a ready example of expounding what machine reasoning is really all about. When humans see soccer players on a field kicking a ball about, they can, with very little difficulty, ascertain that these individuals are soccer players. Today's AI can also make this determination for sure. However, humans can also see a person in a soccer outfit riding a bike down a street, and they would still be able to infer that the person is a soccer player. But today's AI probably won't be able to do this connection because there it lacks reasoning or the contextual awareness of the environment. Without inputted structure, data, and lots of it, there would be no patterns for machine learning systems to identify and make predictions accordingly. Reasoning machines, on the other hand, train on and learn from available data like machine learning systems, but tackle new problems with a deductive and inductive reasoning approach, like just like humans do. So, machine reasoning is the field of enabling machines to understand implicit relationships between different things. For example, consider the following: all animals drink water. Cats are animals. Here, the implicit relationship is that all cats drink water, but that was never explicitly stated. Turns out that humans are really good at this kind of relational reasoning, understanding how different things are related, but not machines are. So, just to this is again from a different paper by Leon Botow. I would say a plausible definition of reasoning, just the reasoning as a concept, could be algebraically manipulating previously acquired knowledge in order to answer a new question. And that's what machine reasoning is all about. All right, so let's see this machine reasoning in the whole thing with an example. An easy way of explaining the value of machine learning is to imagine a just to re-emphasize, I just said machine learning is to imagine a toddler is pushing a phone over the edge of a table, just as shown in this picture over here. Now, without having encountered this situation before, there's no way for the toddler to predict the outcome. But with the growth and learning, he understands what happens. So even if he doesn't completely understands why, that's machine learning at work. So first you need to experience it, then yeah, the machine learns, and now the machine knows that what it has learned. Now imagine that
toddler who was once pushing the glass or the mobile phone off the table now understands the physics of movement and gravity. So that's knowledge, and the knowledge in terms of movement and gravity. Now, even without having encountered this situation before, the toddler can surmise what will inevitably happen. The toddler can apply the same logic to any other object on the table, adapting that knowledge and applying it to a maybe any other object such as glass or of water or maybe a TV remote on the same table, because he knows why it happens. And that's machine reasoning. So this particular reference I have taken from an example, or as a reference from one good blog which I read, and you can find it from the link over here, which I'll mention in the description as well. So moving forward, let's now this particular slide over here. This slide presents a sort of comparison between machine learning and reasoning. Just to mention, these are not two separate components. I would rather see them complementing each other. And well, one may say that reasoning is more closer to the AI and learning is kind of a subset to it. However, having said that, here are certain distinctions amongst these two concepts, and these are merely my own observation. So what I found was that machine learning is more about data, mathematics used around it, such as different kinds of algorithms, statistics, etc., patterns, dimensions of it, etc. However, machine reasoning is not just about data. In fact, it's more about knowledge. It's more about knowledge representation, such as we present knowledge in terms of first order logic, description logic, or many other propositional analysis, or many other fuzzy logic. And there are other ways as well, ontologies, inferences drawn from knowledge, etc. Now, because of these, we seldom say machine learning is about data engineering. However, machine reasoning is more about knowledge engineering. And then there are certain other points, such as the use of these concepts. Machine learning finds its usage primarily in predictions, forecasts, statistical and analytical analysis, for example, in product recommendation, churn analysis, anomaly detection, etc. However, machine reasoning finds its applications more in the space of reasoning, sensing and actuation, problem solving, etc. For example, IBM Watson and Sophia. You might have heard about them. So this is kind of a comparison between these two concepts. Now, this is also an interesting piece which I found from a paper by Daniel L. Silver et al. And refer the citation for the details over here for the paper. And it shows basically how these concepts of reasoning and learning are intertwined or can be intertwined. So let me just put the or recite what was quoted in the paper. The integrated framework is meant to encompass the various methods of machine learning. Eh, Probably we know that what are different methods of machine learning: supervised, unsupervised, or reinforcement, and the various symbolic systems. So symbolic is majorly the machine reasoning part. Now the expert knowledge can be provided by the user to symbolic system where it is retained and or consolidated with existing knowledge. This store of common background knowledge can be used by the inductive learning system as a source of knowledge transfer or inductive bias. In the inductive learning system develops a hypothesis or model using the transferred knowledge and training examples provided by the user. The result is a more accurate model developed in a shorter period of time. The knowledge learned in these models can be extracted back to the symbolic system and retained for symbolic reasoning used by another system or for explanation to the user. So in a way, it's like a overgoing or a kind of an OODA loop concept or a feedback loop concept where we say that there might be an expert feed coming out in a symbolic system in terms of a knowledge. That knowledge is retained, consolidated, and that is a kind of a refined knowledge, expert knowledge, and that goes in the inductive learning system as well. And vice versa, from those training examples or the inductive learning system, it extracts certain knowledge as well, or from those insights we can generate knowledge or the crux of those insights, and that can be fed to a symbolic system as well. And this is a kind of a OODA loop concept where everything goes in a circle and it calls for an improvisation. For more details on this particular picture, you can refer to this particular uh, paper from Daniel L. Silver, and I'll provide the link in the description below. Now let's see with more concrete example, or I just thought of exemplifying this particular relationship, the knowledge and the learning. Now the purpose of an AI system is to make intelligent machines, agents who can think, act like humans do, that is rationally and heuristic. For this to happen, an agent must work just like a human brain does. An human brain continuously learns from its experience, encodes and persists in its memory as knowledge base, just like as we grow from from a very basic stage, the infants, we learn from our experiences, and that or the crux of that or the knowledge out of that we store it in our knowledge base, and then we reason out on different situations out of that knowledge base. Then by using the process of deduction induction, it reuse the knowledge to answer the new questions, and hence the process goes on. In similar approach, an agent with a learning element and a background knowledge can be said to work or at least evolve or dwell in a new environment. For example, Lucy, when visited Brazil, talked to Ferdinand and can conclude that the common language for communication in Brazil or in that particular area is Portuguese. But likewise, she cannot infer that the name of Brazilians is Ferdinand, right? So that's a kind of an inductive process. So by interacting with a fellow who is speaking Portuguese, she inferred part of it, but she cannot or she didn't infer that all of them are Ferdinand. Now there are two other examples to this, as mentioned in the slide. For example, an experienced support engineer, when troubleshoots the hard disk utilization issue for the first time on a new Linux platform, knows which command to issue but could not imply the similar inference for doing the vendor specific troubleshooting, because the engineer knows that there are certain things which are common particular to OS, and that's why he can be sure that if I need to check the say space utilization or disk utilization of Linux OS, so what should be the command, but the application specifics he might not be aware. So this is kind of an inductive or inductive learning process, and the use of background knowledge allows much faster learning than one might expect from a pure induction program. So now I will just like to conclude on this particular slide, which is to it's kind of an introduction to the knowledge based system or the conceptual view of a knowledge based system. So and as shown, every knowledge based system comprises of mainly two components, which is a knowledge base and an inference engine, and both of them should process, or as a comprehensive knowledge based system should have certain characteristics. First, it should be symbolic. It incorporates knowledge that is symbolic as well as numeric, and you will see when we will see further maybe presentations around this subject, the examples of a knowledge base and why I am calling it as a symbolic. Second, heuristic. So as a heuristic, it is a good test to ask the question, what might I do in this situation? And that's how the humans do, or humans are heuristic. We say humans are much heuristic in nature. Third, it should be transparent. Its knowledge is simply and explicitly represented in terms of familiar to specialist and is separate from its inference procedures. So what does this mean? This means that there are, as I said, there are two things: knowledge base and inference engine. Knowledge base could be your domain specific. For example, We can have an intelligent agent, or we can have two people, one is doctor, one is or we can have a same person who is a doctor and who is a father. Now all fathers can have similar database, or similar, sorry, knowledge base, right? Any other fellow who is an engineer can, and a father, can share the same sort of knowledge base as does any other human who is a doctor and a father too. But the other part of it, a doctor's knowledge base will always be different from a engineer's knowledge base, right? But the inference engine over here could be same. So what we are saying is that there could be certain procedures or algorithms which we can write, which intelligent agents can use, and those should be domain agnostic. Second and the fourth and sorry, not second, fourth and the last one is the flexible, and which is the most important one. It should be incrementally refinable and extensible, and that's how the knowledge of humans evolve. For example, for those people who don't keep on learning or who are not flexible, we say that their growth stops after a period, right? And that's how we are saying that a good intelligent agent should be flexible as well, or should have a knowledge based system which should be flexible itself. Now, as I already said, for a knowledge base, it is a set of sentences that describe the word in some formal interpretational or representational language. For example, first order logic, we will see some of it, the concept of first order logic or propositional logic or Bayesian networks or maybe MDP in upcoming presentations. And a logic is a formal language that includes both syntax and semantics. So a logic basically contains, not, it's not just about data, it also carries the semantics along with it. So if I say that there is a sentence called this animal is a cat, right? So this has a semantics as well. It's not just like we have certain columns with cat as a value to a particular attribute. And the inference engine. Inference engine is a set of procedures that work upon the representational languages that can infer new facts or answer the knowledge based queries, and can answer new questions if asked. And it should be domain independent as far as we can comply to it. So, well, I would like to end my talk now, and that's all for now. And just to reiterate, if you like this content, or if you like to view more of such presentations and similar content on the lines of machine reasoning, AI, machine learning, and even IoT, which I'll be adding on in coming days, please subscribe to my channel, hit the bell icon, and give me a like and your feedback too in the comment section. Well, if you don't like it, please feel free to dislike it and give me your feedback as well. That will help me to improvise further. Thank you for watching, and thank you for sparing your time over here. Bye.